Okay, so far we talked and showed some examples for FaceTel and SPN designs, but I told you that there's another, the third method, which is called permutation based. I haven't given you an example because when we're going to talk about authenticated encryption, I will show you a standard named ASCON, and I will show you how you can use a permutation based or sponge function design to design a block cipher. But before that, and I mean, SHA-3 hash function is also a sponge function, by the way. So until those dates, people were always designing ciphers using FaceTel or SPN approach. So let's look at some basic differences between them. The pros are as follows. In the FaceTel, encryption algorithm is identical to the decryption algorithm. Only the order of the round keys change. So this is super nice. On the hardware, you only implement the algorithm. For encryption, you use the round keys in the original order. For decryption, you just reverse the order and you obtain a decryption. This is very nice. And the good thing with the SPN is that a single round affects whole input. Recall that in the FaceTel structure, only half of the input is modified. The half remains the same. So this sometimes the confusion and diffusion becomes slower on FaceTel ciphers. But the cons are just the opposite of these things. In FaceTel, a single round only affects half the input. And for the SPN, the decryption procedure requires the inverse of substitution and permutation layers. But this sentence is not valid if your mode of operation turns the cipher into a stream cipher, okay? So when we talk about mode of operations, this will be more clear. Because in that scenario, you will always use the cipher in the forward direction when doing encryption and decryption, okay? So another design consideration is hardware versus software, because sometimes you design the cipher on a specific platform. So if it is on hardware, you can easily put operations that work on bits, like in the case of present, because on hardware, it is very easy to work on bits. But on software, most programming languages focus on bytes, and bit operations are more costly on software. So this is why CLEFI is generally preferred for software and present is preferred for or suggested for hardware. Cipher design also determines the number of gates required to perform encryption on hardware. Number of gates determine the area required. So you might want to design something small, but this can be done by putting easier operations or non-complex operations, but this also makes the cipher non-secure, right? So you have to find a balance between these. Also, code size or required memory is not a big problem for software implementations due to fast CPUs and large RAM, because in our modern, it doesn't have to be a laptop, even Raspberry Pis, our mobile phones have multiple cores, gigabytes of memory. So you don't care if your code, requires a few hundred bytes of memory, right? But in some very small devices, you have to work with even as small as 64 bytes of memory. So you have to come up with a design or algorithm that requires very small amount of memory, or the code sizes should be really small. So these are your design considerations. Another consideration is security versus speed. So speed is generally measured as throughput. And adding more security measures, for instance, increasing the number of rounds increases security, but reduces the speed. So this is a problem. If you design your cipher 20 rounds and then increase it to 40 rounds, yes, it might double the security, but halve the speed, right? Also, in some of the weaknesses, some of the cryptanalysis techniques, the attack works regardless of number of rounds. Okay, so increasing the number of rounds doesn't always mean that it increases the security. And ciphers performing well on hardware or software may not be suitable for constrained devices, for RFID systems or sensor networks due to limited memory, battery, or computational power. This is why AES is not the solution for everything. Sometimes we need lightweight ciphers, okay? So let me go back to our initial topic, which was about the key size. So what should be the key size? So an attacker that captures a single ciphertext can try to decrypt it with every possible key and then check if the resulting plaintext looks meaningful. So this is actually called exhaustive key search or brute force attacks, in which you try every key one by one. So exhaustive search is a generic attack. This means that it is valid for every cipher. So here you're not using any weakness in the cipher design. You simply take the cipher and try every key one by one. So for a k-bit keyed cipher, the attacker is required to perform at most 2 to the k encryptions or decryptions. Thus, security of a block cipher is upper bounded by exhaustive search, in other words, by 2 to the k encryptions. This quantity is referred to as time complexity. Okay. So here, of course, if you capture the plain text block and the ciphertext block, it is even easier. You encrypt the plain text with every possible key and check if the desired ciphertext is obtained. Okay. So this can be done for every block cipher. So then the question is, how large should we have the key? Yes, right? So for this, I told you that that value of k is 56. So in the worst case scenario, you have to perform 2 to the 56 encryptions to break this. And 2 to the 56 is this number. So, but if you increase the key size like present and choose the 80-bit key, since these numbers are increasing exponentially, as you can see, the digits are also increasing in a very fast way. For instance, for AES 128, this is it. And for 190, by the way, nobody uses 192. It is even in papers when we find attacks for all key links, it doesn't fit the in page limits. So we generally put the 192-bit version at the appendix because in the world, nobody uses it anyway. You either use 128 or 256. So as you can see, reaching to military grade security increasing the key space to an enormous number. And sometimes people cannot comprehend how large this number is because we are simply talking about 256 bit, right? When you look at 256 zeros and ones, it doesn't look really large, but the whole space is 2 to the 256. So we don't have actually point of measurement to understand how large it is. But you can look at the problem like this. In the observable universe, the number of atoms are close to this number. So just imagine performing an encryption for every possible atom in the observable universe. So this number is as large as that one. And also, I already told you that 56-bit, we can do these operations in short time. Actually, with CPUs, you can do 2 to the 20 encryptions in a second. This is easy. You can even reach more, and you have a lot of cores. But at the GPU side, on a high-end GPU, you can perform 2 to the 35 encryptions per second. Okay. So actually, you can break this less than a year on a single GPU. But this means that if you have hundreds or thousands of GPUs, you can start to break this in minutes. Or if you have huge data center, you can even break it in seconds. So sometimes saying that short key provides short-term security, we have to be clear on how short are we talking about. Because if you need security for a week, and people can break it in months, this is bad because they will always increase their capacity and start breaking in weeks in short time, right? So this is why we have to be clear about what kind of security you need. And actually, there is no need to reduce your security lower than 128. Also, since we are always getting better equipment, GPUs get with better cores, higher clock speeds, etc., or you can build your own devices. I mean, if you optimize on hardware or FPGAs, you can burn it into silicon and build ASICs, which are dedicated devices only to do this operation. For instance, for Bitcoin mining, we have ASICs. So nobody can actually mine Bitcoin using CPU, GPU, or FPGAs because ASICs provide a lot better speed with a lot less electricity, right? So this is why if your aim is to break something and if that will be profitable for you, you don't mind, using a factor to build a dedicated hardware for you. Of course, you need the money to do that. But at the end of the day, assume that our technology improves so fast that we can perform 2 to the 80 encryptions per second by using all of the computational devices on the Earth, okay? So this might give you the illusion that then this key length is also now insecure, but if I can perform 2 to the 80 encryptions per second using everything on the Earth, every computational device on Earth, I cannot still break 2 to the 128. I mean, I cannot break this key length, because if I can do this in a single second, 1 year has around 2 to the 24 or 25 seconds. So this means that I have to perform 2 to the 23 years of encryption anyway, which is 8 million years. So if you can run those devices for 8 million years, then you can break and capture a single key. I mean, of course, if you can live that long and pay the electricity bill, why not? So this is why breaking this doesn't mean that we can also break these key lengths. Of course, by brute force. If you can find a weakness, maybe you can break it faster. So another question that we ask, how many runs a cipher should have? There's no direct answer. The common belief is that increasing the number of runs increases the security. However, it will decrease the performance. A common practice is as follows. Designers apply every known cryptanalysis techniques, and if they can break n runs, then they choose the run number RS. R is larger than or equal to 2n to stay on the safe side, because attacks always get better. Okay, this is just a common practice. It is not a scientific solution to a problem. Okay. So here's a list of some standardized block ciphers. At the IOC side, we have many block cipher standards. And below this line, we have lightweight standards. So initially, only Present and Clefairy were in the standards. I think they were chosen as standards in 2012, and a few years later, Leah was added. But although there are a lot of standards at IOC side, for instance, height can be considered broken. And when you have AES, I don't see any point of using actually the others. On the NIST side, the things are a little bit different. NIST had 3 block cipher standards. Skipjack was designed by NSA and has 80-bit security. So it is no longer used, but you can only use it for backward compatibility in order to decrypt something that was encrypted before. So it is no longer in the standards. Triple DES, NIST said that 112-bit security is enough for until 2030, but they said that they removed triple DES in 2024. So triple DES is no longer an American standard. As I told you before, some of the credit cards use triple DES when they do contactless payment. So NIST only has AES. And in 2023, they chose ASCON as the lightweight block cipher standard. And it also provides authenticated encryption. But their argument is that they don't look as the problem as having 2 block cipher standards. How they look at this thing is that they suggest using AES whenever possible. If for some reason you don't like the performance, or if it is not suitable for your case, then you can choose to use ASCON. This is their approach. And although it won the competition in 2023, we still don't have the final version of the standard. Okay, it takes sometimes years to prepare this kind of stuff. And also in the competition, their initial design had a 64-bit block size, and they suggested 128-bit block size version as an alternative version. But after they won the competition, NIST chose the block size to be 128 bits. So during even the standardization process, some choices might be changed. So this is why it takes some time. So all of these algorithms have no patents, so they're free to use. You can simply implement them and use them. This is the good thing. So let's finish with some of the problems that we observe when we use block ciphers. One of them is key management. Keys must be exchanged between the communicating parties before they can use the block cipher. But the problem is that to communicate with n people, you have to exchange securely n keys, which is not that easy, right? Think about having a lot of IoT devices and putting different keys to all of them. So this is not easy. One solution is using public key encryption algorithms, but they are slower than block ciphers because their performance is lower, and also the data size increases when you do the encryption. So this is not something preferable for IoT cases or lightweight scenarios. You can also use key exchange algorithms like Diffie-Hellman key exchange. But again, maybe your device is so small that you wouldn't want to put a implement Diffie-Hellman on it. So you have to come up with a better solution, which is sometimes manually, getting the device, changing the key and putting on the field, etc. Second thing is, how do we store the key? Storing keys directly on the hard drive or RAM can be a problem because with the attack, if there's a Trojan or malware, then they can be captured. So you can have different solutions like tamper-proof hardware, etc. But still, this problem is not that easy to be solved, okay? It depends on the context. Third one is message length hiding. Plain text and corresponding ciphertext lengths are identical because if you encrypt your 1 megabyte file, the ciphertext is also 1 megabyte. But if the adversary knows the context of the communication, then they can guess the plain text just by the ciphertext length. Here's an example. This is generally what people do. Some websites encrypt the forms filled by the users, but the remaining parts sent unencrypted. An example from a medical form can be like this. So the question can be, did you ever have a surgery? So if yes, provide details. So your answer to this question can be understood from the ciphertext you sent, because if the user answer to this question provides a short ciphertext, namely one block of encryption, probably you answered as no. But if it is longer, then you probably answered as yes. So just because of looking at the ciphertext length, you can get the info from the context. In the past, we did some work on this by adding some random unnecessary stuff to the end of the message, but the length of this random message depends on, selected randomly. So this way you try to hide the message length. You can, if you're interested, you can look at it, which can easily be, by the way, combined with the TLS implementation if you want. Another question, key generation. To obtain k-bit security, the k-bits should be generated randomly. This is important. So generally, if you want to put a backdoor, you put your backdoor to the random number generator so that you know from which set the person you are attacking is generating their random number. So you reduce it somehow. Or if even better, this happened in the dual elliptic curve random bit generator. There was a backdoor in, so when you use it, the attackers know which random numbers you are going to produce in the future, and they can go backward and capture all of the random numbers you produced in the past, okay? So this is why NSA wants to put backdoors to all of your algorithms, and this is how they did it. So this was a RSS standard, NIST standard, and then after Snowden documents, people found the weaknesses. Okay, one solution is to use using cryptographically secure random number generators or password-based key derivation algorithms. Again, it depends on the context, how to use them, and But for example, for full disk encryption, you can use a password-based key derivation. So as long as you remember password, you can reproduce your secret key and then encrypt your hard disk or decrypt it back.